Hi, this is Dr. Chamberlain. I am going to make a little video answering the first three ranking questions. So in this first question, it says that there's 6 types um, of waves that have equal wavelength and they're in the same medium. And it's asking me to rank according to their energy. So it doesn't actually matter, but it's important to kind of think about what we're dealing with. So they do tell us that there's equal wavelengths here and same medium. Same medium is telling you that the tension of the string will be the same or the density of the air, and so that is a clue um, that the speed is the same, and the equal wavelength is just saying the wavelength is the same. So it doesn't actually matter though, because energy, the average wave energy in the medium has to do with amplitude. And so no matter what kind of wave, that is related to amplitude. So all we're doing here is we're just ranking the amplitude. Amplitude, remember, is the maximum displacement from the equilibrium. So it's this amount right here. And we're just going to use these pictures and just kind of do our best. You might get out like a little pencil or something to help you. So the highest energy is the highest amplitude. So I'm going to say that's like A. Kind of looks like A and B are the same, and C, maybe those are all the same. And then I would say E and F. I'm not using like a little measuring device. So if you find that like C is maybe more the same height, C looks like A and B. All right, so that is the first ranking task. All right, this one is a completely different concept. In this case, we're looking at superposition when waves overlap. And so here we have, um, they are different pairs of waves. They're rectangular, it just makes it easier to picture what's going on. And they vary in height and length. And at some point, they're interacting with each other. And they're asking about the maximum height of the combined wave or the combined pulse. Um, so that would be like the most that it could possibly be, and we're ranking that. And so when waves combine, so if you have this wave combining with this wave, when they meet in the middle, you're going to be adding the amplitude. So this disturbance and this disturbance are adding together, and it could give you that kind of disturbance. The width here does not matter. It just means that what this would look like is maybe more like this kind of a wave. But since all they're asking for is the maximum peak height, we don't care about the width. So we're just looking to see how they could add together. Now I will note when you have something down below, it's going to be subtracting it. Basically, this is pulling, if this was a string, this is pulling the string up, this is pulling the string down, and they would counteract. So that's actually 0. All right, so to go ahead and rank these, this one and this one look to be about the same. So A and C are pretty good. And then I would say B is the next one. And B is maybe the same as F because B has that like extra, no, B is not the same as F. I think F is a little smaller. But F and D, I think would be the same. Yeah, F and D are the same. And then E is 0. All right, so there is that ranking. Let me clear this up a little bit because I kept drawing on. Okay, so it is A equals C, and then B, F equals D, and then E. Okay, this last one, again, another concept here, we're talking about frequency, which is a lot similarly related to period because they're inversely of each other. And so if you kind of understand one, then you can understand the other by realizing the inverse relationship. Okay, so this is a standing wave. This is kind of a core concept of what we're doing. A standing wave and a string, so which means it's reached this harmonic, and the string is kind of doing this special thing where it's just kind of going back and forth, and you have these areas called nodes right here where this string is actually not moving in this node because of the superposition. So this pulse is going through and it's trying to pull the string up, but this pulse is going through and it's pulling it down. And so what happens when they meet is nothing moves. Okay, so we're ranking based off the frequency of the wave. In this case, period's not really going to help us because we don't know about the time, but we also know that for a constant speed, the frequency times the wavelength is a constant number. And the speed depends on tension. So we want to make sure that these have the same tension. Same tension. Okay, cool. And all strings are identical. So that tells us they have the same like mass to length ratio and the same tension. So this is the same. So therefore, if we're ranking based off frequency, we're also ranking based off wavelength, and that's going to be really kind of what we want to look at here. So the greatest frequency would have the least wavelength, and that would just be the smallest. So this has a pretty big wavelength. This is the wavelength here. It goes up and down. This is the wavelength here. This is the wavelength for this one. This is the wavelength for this one. Those look similar. This one and this one. Now the lengths here are different. I think that they are scaled so we can just do a visual. But if you really wanted to get fancy, you would calculate the number of waves in the length, and you could actually calculate the wavelength. So in this case, you have, so for F, 1.5 wavelengths equals 30 centimeters. And so then the wavelength is going to be 30 centimeters divided by 1.5. I'm not going to do that. I'm going to just eyeball it. But if you have done this and you differ a little bit from me, then that's great. You are more correct. But I'm just thinking of the concept here, and so I'm just going to eyeball it. So I'm going to say the least wavelength is A, B, and E. They kind of, E is probably smaller. E and A and B. B is going to be a little bit bigger. All right. Maybe, I don't know. Maybe you should calculate it. But this is roughly what's going on. And then I have D and C and F. Okay, so again, so you can calculate it to get perfect, but the concept here, which is what you'll be tested on, the concept is looking at that length of the wavelength, because you know wavelength and frequency are inversely related for constant speed. All right. Okay, just do this calculation in my head. And it does look like B is smaller than A. So I think that is what we have there. All right. Good luck with the rest of the problem set, and I look forward to seeing your solutions.